Hi, good morning everyone. Today we are learning the lab 4 called the Laplace Transform. Okay, we continue to the last one. Last time one is a Fourier Transform. So what is transform again? So it, like the Transformer movies, the Autobots from the Cybertrons, called the Bumblebee, the yellow color this one. It transformed to a simple vehicle like this one. It's called a Volkswagen Beetles via the sophisticated machinery transformation. So it changed the appearance to from one to another without changing the original properties. So how about the Laplace transform? So unlike the Fourier transformation as the previous lab, this transformation which the transformation of the time domain signal Vt into a frequency domain Vf or V omega. So for the Laplace transform, so that we transform the time domain signal to the S domain for the continuous time system. So like this one is a Fourier transform. Last time we learned. So this one is a time domain. This one is the signal we see from oscilloscope. Oscilloscope signal normally is a display the time domain. The signal varies as time goes in the horizontal axis. So from this time domain we can convert to the frequency domain. Means the signals, the amplitude signal and the position of signals here is depend on the frequency of the signal. You see, this one the frequency lower frequency, this one higher frequency, the pink the magenta color. So this blue color is even higher frequency. So higher frequency will locate the further apart from the origin. So the lower frequency will locate the nearer to the origin here. So the amplitude here is the amplitude actually is the amount of height of the amplitudes of the waves here. See, the wave here is higher, the amplitudes here. So this one actually is higher. So this is called a Fourier transform, as last week we learned. But this week we learned the time domain signal, like this thing, time domain signal, convert to the S domain. S domain means I have the 2D plot here. So the x-axis here is the sigma, small letter of sigma. So the y-axis here is the j omega, means the imaginary axis. So in this plot we have few components. The first component we call it as pole. The pole here is represented by a cross here, and another component here we call a zero. These things, this pole and zero here, actually they can move everywhere, depend on the equation of your Laplace transform equation. Okay, we will see later what is this, why is rocket here, why is rocket here, what is this, we will see. So why transformation is needed? Like for example the transformer, the Bumblebee, Optimus Prime and the gang can transform into a vehicle. You see here, they can transform to a vehicle so that they can depart together to find their enemy. What is the purpose for the Laplace transformation? So it's make the time domain differential equation, time dependent differential equation or integral equation of the linear system easier to solve with or work with. Means if let's say I have a time domain, you see, time dependent signal at here, t here. So sine of at actually we transform in the Laplace domain, means the S domain. They are called a divided by s squared plus a squared. This thing you can from time domain to S domain, you see the S here. So and also the S domain plot allows the direct system stability prediction before convert into a time domain. Okay, you can see from here. If we see this graph, so actually we can determine how the system will work. The input signal like this one, I shoot the input signal into the system, then I can predict the output. Let's say I have this pole here. You see the cross here actually represent the pole. If the pole is located at the left hand side of the S-plane, So the system, if I shoot a unit step inside to the system, so the output will become damped, become slowly go to 0, even though initially have signal variation. So if let's say the pole sit on the x-axis here, the real axis at the negative side, so the signal also will go towards 0. But if let's say the pole is sit at the right hand side here, so if I give a unit step to the input here, then the output will gradually increase until the system is very, very unstable. So if let's say the pole is sit on the real axis at the positive side, so the output signal also will increase until very unstable. You see, this is unstable region. The right hand side is unstable region. The left hand side is unstable. This graph S-plane will let you understand how the signals how the system behave if I use the input normal step signal. Okay, unit step signal. Sorry. So this is a summarize. You see, at this point, if the pole sit at here, then this one will go down as this one. If let's say the pole is sit on the y-axis, sit here means, so the output will generate a sinusoidal waveform, or stable, is a marginally stable, we call marginally stable waveform, because this will oscillate up and down, up and down, and this one oscillate from up down, but finally will damp up, means become 0. Okay, this is a function of the S domain graph. So actually we can, what is the purpose of transformation? We need to transform the time domain signal into an easier interpretation signal in S domain. So we see, if after the transform we see this pole here, then we know what is the properties of the system. Okay, so inverse transformation. Why we need inverse transformation? For example, for the transformer example, the Volkswagen Beetle, this one, see, or the Chevrolet Cameron, this one, the last time one, the new movie, is transformed back or inverse transform. We call it inverse transform. We transform back from car to robot back into a bumblebee, so that can physically communicate with human. Means you can talk with this girl, or we fight with the enemy. Means in the robot shape, they can fight with the enemy in robot shape. It's not car. Car cannot fight. The robot can fight. Similarly, the inverse Laplace transform turn the soft result, means the S domain, the result here, back into the time domain, mathematical time domain representation, so that the human can easily interpret. Means initially you transform the time domain signal to S domain, then you do the calculation, you solve the calculation using the normal mathematical methods, the polynomial methods. Then you can, after you solve the equation, then you transfer back, or you inverse transformation back to the time domain signal. Okay, so that your result is very easily solved using the transformation, using this transformation. If not, then it's very hard to solve. Okay,